So, student, today I am going to discuss about the second law of thermodynamics, thereby the working of heat engine, heat pump, and the refrigerator. So, before going to second law of thermodynamics, I like to highlight the first law of thermodynamics. So, according to the first law of thermodynamics, the heat and mechanical work are mutually convertible. So one can be converted into another. So for this first law of thermodynamics, there are few limitations. These are like this. That from the first law of thermodynamics, this conversion, suppose the heat and work, these are the two forms of energy. So whether the heat can be fully converted into work or whether the work can be converted fully into heat. So this conversion actually it is not specified from the first law of thermodynamics. And second thing, that the direction of heat flow, direction of flow of heat and work. So say heat and work, these are the two forms of energy. And if we say the heat, so whether the heat it is flowing from hot body to cold body, or whether this heat it is flowing from cold body to hot body naturally, so it is not specified from the first law of thermodynamics. And also the condition it is also not specified from the first law of thermodynamics. So basically these conversions or this direction of flow, it will be clear to us from the second law of thermodynamics. So basically for the second law of thermodynamics, there are two statements. One is Kelvin statement and another is Clausius statement. So basically, Kelvin statement, you can apply this statement for the heat engine, for the working of the heat engine. And for the Clausius statement, you can apply it for the working of the heat pump or the refrigerator. So now, coming to this statement and the working of this heat pump refrigerator. So, from the Kelvin statement, according to the Kelvin statement, it is impossible to construct an engine working on a cycling process whose sole purpose is to convert heat energy from a single thermal reservoir into equivalent amount of work. So basically, we can apply this Kelvin statement for the heat engine. So basically, for an engine, say if it is a heat engine, so it is difficult to construct a heat engine that is working on a reversible cycling process, and this heat engine actually which is taking heat from a single thermal reservoir. Okay, the engine actually is difficult to construct, which is only taking from a single thermal reservoir, taking heat, and then this engine actually it is impossible for this engine to convert this heat which is taking from the single thermal reservoir into equivalent amount of work. So basically, it is impossible for a heat engine. So how it is possible to construct an engine? So say it is our heat engine. So this engine actually, if you deliver this heat actually from this engine, actually heat engine is something which, if we give some amount of heat to this engine, so this engine can convert this heat into work. So basically, this is the working of a heat engine. So basically, for a heat engine, it is difficult to construct. Actually, difficult to construct this heat engine if this heat engine only taking or working with the single thermal reservoir. So now we are taking two thermal reservoirs instead of single thermal reservoir. So what is high thermal reservoir? Say this temperature of this thermal reservoir, it is T1. You know what is thermal reservoir? Basically, thermal reservoir, it is a large body of infinite heat capacity. If we take or give some heat to this body, so the temperature of this body, it is remain the same. So basically, this heat engine are working between two thermal reservoir. One, the temperature, it is high temperature thermal reservoir, and another, it is low thermal reservoir, and the temperature of the low thermal reservoir is T2. So now this engine, it is working between two thermal reservoir, and basically from this high thermal reservoir, if we are taking some heat, say it is Q amount of Q1 amount of heat. So basically, this heat engine cannot convert whole the heat energy to equivalent amount of work. Basically, these conversions we can get it from the this kind of conversion you can get it from the study of Shadi Karna. According to the study of Shadi Karna, that heat, it is a low grade of energy, and the work, say if it is a W, so it is a high grade of energy. So the complete conversion of low grade of energy into high grade of energy, it is impossible. But the high grade of energy can be converted into low grade of energy fully. So basically, this it is stated by the Shadi Karna. So basically, for our heat engine, basically this heat which we are supplying to this engine, so engine cannot convert all the heat into equivalent amount of work. So say some part of heat is converted into work, so that is W, and the rest of the heat, it is rejected to the low thermal reservoir, or we can say it to the sink. So now it is possible to construct this kind of engine. So it is our heat engine, and basically this heat engine, it is working between two thermal reservoirs. One is high thermal and another is low thermal reservoir. And basically this heat engine, it is not converting all the heat into work, as the heat is low grade of energy. So low grade of energy, it is not possible to convert fully into high grade of energy, that is into work. So basically some part of heat it is converting into work, and the rest of the heat, say it is Q2, it is rejected to the same. So if you will get this in the next slide, it is our engine, same thing what I have stated in my earlier slide. So basically this heat engine, it is possible to construct, which is working between two thermal reservoirs. It is taking in T1 and it is converting some part of it into work, and the rest of the heat it is rejected to the low thermal reservoir. So now, if we like to measure the performance of this heat engine, so basically with the help of the efficiency, thermal efficiency, we can measure the performance of this heat engine. So you know the efficiency of the engine is output by input. So what output we are getting from this engine, that is work. So amount of work from here we can get, that is P1 minus Q2. So this amount of work we can get it from this engine. And what input we are giving to it, that is P1. So now the thermal efficiency of this heat engine will be like this. That is output, the work we are getting from this engine, and the amount of heat, that is the input which we are supplying to this engine. So you can write it here like this, that is Q1 by Q2 by Q1. So it is the efficiency for any heat engine. So as no heat losses is there and no friction losses is there, basically this engine is working on reversible cycling process. So this efficiency is the maximum efficiency, and basically this efficiency is equal to the Carnot efficiency. So according to the Carnot efficiency, you can write it like this: P1 minus T2 by Q1. So it is the performance for a heat engine. So now for the next Clausius statement, it is the another statement from the second law of thermodynamics. So according to the Clausius statement, it is impossible for a self-acting machine, okay, self-acting machines, and the machine which is working in a cyclic process to transfer the heat from a body at what temperature to a body at high temperature without the aid of an external agency. So actually from this statement, the direction of heat flow will be clear to us. Okay. So basically, from the first law of thermodynamics, it is not specified that whether the heat it is flowing from hot body to cold body, or whether the heat it is flowing from cold body to hot body. So basically, what happens? Heat it is flowing normally from hot body to cold body, like the water. Suppose some amount of water can flow naturally from high point to the lower point. So basically, heat flows normally from the hot body to cold body, but heat will not flow normally, or can say naturally, from the cold body to hot body. So direction of heat flow it is clear, will be clear to us from the statement. So suppose it is our machine. This statement actually. Suppose it is a self-acting machine, and basically this machine is actually it is working in a cyclic process. So actually these machines, the machines cannot transfer the heat. Okay, suppose it is a body of what temperature? It is a body of what temperature, and it is a body of high temperature. So for a machine actually, it is impossible to transfer heat from the cold body, from a body of what temperature, that means we can say cold body, and to transfer it to the high body naturally, unless and until we are taking the help of an external agency. Means if we are not putting or if we are not supplying some amount of power, then it is not possible to take the heat from the cold body to hot body. So actually this is the second statement, actually Gaussian statement, and we can put this concept, or we can put this statement for the heat pump or the refrigerator. So I am coming to this later. So for the heat pump or refrigerator, these are the devices actually. This follows the second law of thermodynamics, and basically the direction of heat flow will be clear to us from their working. So basically, heat pump and the refrigerator, the objective of these two devices is same. Actually, both these are both these will transfer the heat from the lower body to higher body. So for the heat pump and the refrigerator, both these are the lower body. So from this lower body, the refrigerator heat pump will transfer this heat to the higher body. So this is the higher body for the both of these devices. Heat pump and the refrigerator. So now I am coming to this heat pump. So basically, what heat pump does? So heat pump is a device which helps us to maintain the temperature of a room. Say if for our room, for the winter season. For the winter season, if we like to maintain, if we like to heat our room, then we can engage a heat pump, and the heat pump simply can extract the heat from the surroundings cold body, and then the heat can be supplied to our room. So then our room will be heated. So this is the function of the heat pump. And the refrigerator, basically refrigerator is a space in our room where we like to maintain the temperature of this room below our room temperature. So basically the objective is same, but the purpose is different. So for the heat pump, say it is our room. Okay, so it is our room, and the surroundings of our room, that is the atmosphere, it is our lower temperature. Suppose in winter days actually we use some heat pump. So basically this heat pump it is unable to flow the heat naturally from the cold body from the atmosphere to our room. Some kind of external agency or some kind of work, some kind of work it is need to deliver to this heat pump. So say this is the atmosphere from here. Q2 amount of heat it is extracted by this machine. So when we are giving W amount of work to this heat pump, then this heat pump will supply Q amount of heat to our room, and then our room will be heated. So basically, this is the useful output. This is the useful output for our heat pump. So now, if we like to measure the performance of this heat pump, so basically the performance of this heat pump it is measured by COP, that is known as coefficient of performance. Okay, so coefficient of performance. So coefficient of performance for the heat pump will be like this. That is the amount of heat it is delivered to the higher body. So that is the Q1. So Q1 by the amount of work which we are putting to this pump. So amount of work means W. So next we can write here that is Q1, and the W means we can write here that is Q1 minus Q2. So it is the amount of work it is need to be delivered to this heat pump. Otherwise, the heat is not will flow naturally to this higher body. So W is equal to, you can write here that is Q1 minus Q2. So that is the coefficient of performance of the heat pump. And in the next I can tell you that as this heat pump is working on cyclic process, reversible cyclic process, so no heat losses or no friction or kind of losses is there. So basically this COP it is a kind of maximum COP, and basically we can write it here T1. So it is the expression for COP of a heat pump. Now I am coming to the refrigerator. So already I have stated that refrigerator help us to maintain the temperature of some space below the atmospheric temperature. So say it is the space in our room, okay? It is the space in our room, and we like to maintain the temperature of this space below the room temperature. Suppose we like to maintain the temperature of this room at T2. So for this, what it is need to done, always we need to extract some amount of heat continuously from this system, from this space. So for this, actually, so to transfer this heat from this lower space, lower temperature space, we need to engage some external agencies, and basically we need to engage some kind of devices. You can say refrigerator. And always some amount of work is need to be delivered to this device. So say for extracting Q2 amount of heat continuously from our refrigerator space, W amount of work we need to done for this refrigerator, and for this the refrigerator it is rejecting Q1 amount of heat into the room, basically the atmosphere. So basically for the refrigerator it is our useful output, but for our heat pump it is our output, useful output. So if we like to measure the performance of this refrigerator, so basically it is also expressed by COP, that is COP, coefficient of performance of the refrigerator. It is mean the amount of heat we are extracting from the cold body. So Q2 by the amount of work that is we are delivering to this device here, that is W. So you can write it here. The COP for a refrigerator is equal to Q2 by W is equal to, you can write it here Q1 minus Q2. So Q1 minus Q2. So again, as no losses is there, that is working fully on reversible cyclic process, so we can write it here T2 by T1 minus T2. So it is the expression for COP of a refrigerator. So now I can tell you that as basically if the same device it is working or it is performing both of these heat pump and the refrigerator. So for these cases we can write it here for the devices actually COP of the heat pump is equal to COP refrigerator plus 1. So basically COP of the refrigerator it is always greater than unity for any device which is both performing the heat pump of the refrigerator. So basically I discussed about the first law of thermodynamics and the limitations, and from the limitations actually how the statement of second law of thermodynamics we are applying this for the heat pump and the refrigerator. So I like to end my class here. So thank you, students.